Here's an idea you're familiar with. The locus of an equation is the set of points whose coordinates satisfy the equation. In this case, the locus is a conic, in fact a parabola, and here are two typical points. When x equals a, y equals plus root a satisfies the equation, and so does y equals minus root a. Well, that's for real variables x and y. But what's the locus look like when we take complex variables w and z? Or in general, what does the locus look like of an arbitrary complex quadratic equation or conic? Well, even with w squared equals z, there's a problem. We have to replace the x and y axes in this picture with two planes of complex numbers. So the locus lies in a space of 4 real dimensions, which evidently we don't have. What we're going to show you in this program is a way of picturing some of the information in a complex locus without using 4 dimensions, just 3. In fact, as you'll see, the locus turns out to be only 2-dimensional, so we actually get a very good picture of it in 3 dimensions.
The way we picture the locus in 3 dimensions is we use 2 dimensions for z, but only 1 for w. In other words, we represent the domain, the z-plane, correctly as a plane, but we make do with the one remaining dimension, height, for w. For example, take an arbitrary non-zero value of z. Call it z0. Then there are 2 distinct square roots. Call them w1 and w2. And we put the points of the locus, like this, vertically above z0. So although we can't represent the w coordinates correctly, we've only got 1 dimension for w, we make sure that different w values are represented by separate points of the locus. And that's what we'll do above each point of the z-plane. Actually, as z0 varies, we don't take completely arbitrary heights. We take some account of how the w values vary. To see how, let's take z0 and run it round a circle centre the origin of radius r.
So z0 equals r e to the I theta, where r is fixed and theta varies from 0 to 2 pi. Therefore, the values of w are these: root r e to the I theta by 2, and minus it, which you can get by writing a pi here instead of the minus sign. To see how we draw the locus above the z circle, let's look first at these red roots. As z traces out its circle, w1 goes continuously from plus root r round here to minus root r. So it starts at 1 square root of r and finishes up at the other root.
We draw the locus for those roots like this. We put each root vertically above its value of z, and we draw the diagram as a spiral, so the 2 roots above r get separated. Well, this is the only point for which we've shown both the roots. What about the other ones?
To get the other roots, we can actually stay with our first formula and go round the z circle again. We just have to add 2 pi to the values of theta. Therefore, what we have to add to the values of theta by 2 is pi, which gives us the other roots. We just carry on round from minus root r back to root r. So the 2 roots of r swap back again, and we end up with the root of r that we started with.
So we draw the locus like this. We continue the spiral all the way round. Notice that we have to identify the 2 red ends because this is the same root that we started with. So in fact, this is a topological circle once we do the identification. So we've done what we promised. Above each point of the Z circle, we've put the two corresponding points of our locus, corresponding to the two W values, the two square roots. In fact, we've done rather more. We've managed to show how the square roots vary continuously as Z goes round the circle. For example, supposing you take this value of Z and this black square root. Then as Z goes round, the square root goes continuously round to here, dropping down to here because of the identification, and we end up at the red square root. So the roots swap when you go round the Z circle. And if you go round again, then they swap back. Well, that's just one circle of Z values. What about other Z values? Well, if we take another circle, we'll obviously get the same behavior. For example, if we take a smaller value of R, then we can represent the corresponding bit of the locus as a tighter spiral like this. And if R varies in an interval, then the spirals will fit together and we get this sort of parking ramp surface. Of course, we still have to identify the endpoints on these two edges. So in fact, this is just an annulus topologically. So our locus is already beginning to take shape as a surface. And we can take this outwards as far as we like, and also inwards, although we'll exclude Z equals 0 for the moment, because we haven't studied that yet. And we get what's called a two-fold covering surface, because it covers the Z plane minus the origin exactly twice. Anyway, that's the locus everywhere except Z equals 0. What happens there? Well, at Z equals 0, the equation gives only one value of W. W equals 0. So there'll be only one point of the locus above Z equals 0. So as the radius of the Z circle shrinks to 0, these spirals shrink towards a single point corresponding to W equals 0. So the locus looks like this near Z equals 0. This is the region of the locus lying over a disk centre Z equals 0. We've just taken the parking ramp surface and extended it inwards towards one value of W over Z equals 0. As before, these dotted red edges have to be identified. So this region of the locus is in fact a disk. Just unwind and glue the edges. Of course, when you unwind this and glue these edges, then you no longer get the locus points above the corresponding Z points. So as a locus, we have to show a cut disk like this with edge identifications. But don't get the idea that this cut has to be above the positive real axis. We positioned it here only because we chose to go round all our circles starting here. If we'd chosen to start here instead, we would still have got a disk, but the cut would have been in this position instead. It doesn't make any difference because these edges are identified, so it's still a disk. So our locus is a surface, even at Z equals 0. It has a disk-like neighbourhood there. Later on, we'll look at a different quadratic in Z and W, whose locus is not a surface. It has a point which gives a single root, but around that root, the locus looks like this. Two disks pinched together at the one root. And this isn't a surface because that point doesn't have a disk neighbourhood. When we do get a single disk wound round like this, we call the point a branch point. Well, so far we've only shown the part of the locus above a disk. But it's easy to see what it's like for the whole Z plane. As the radius of the disk increases, we get larger and larger disks for the locus. And so the locus is also a plane. So we haven't actually got a compact surface for the locus. And compact surfaces are what you're used to in this course. Well, the z-plane isn't compact either. Let's compactify that first.
All you have to do is add a point at infinity to the z-plane, and that turns the plane into a sphere. Remember how that works. You define a new variable, z tilde, equal to 1 over z. And you take the point z equals infinity to be z tilde equals 0. And then to see the z sphere, just consider unit disks in the z-plane and the z tilde plane. The unit disk in the z tilde plane can be thought of as these points in z. So these are the z points with modulus greater than or equal to 1. So the interior of this disk represents all the points outside this one, plus the point z equals infinity. So if we glue these two along their common boundary, we get the whole z-plane plus the point at infinity, which gives us a sphere. Two disks glued together along their common boundaries. So that compactifies the z-plane. Now we have to see what the locus looks like at z equals infinity. That is, we have to find the values of w at z equals infinity. So we substitute our new variable and look for values of w at z tilde equals 0. Well, there are no finite values of w here. So we use our substitution trick on w and get this equation. The same equation we started with, but with the new variables. So as before, there's only one value of w tilde at the new origin, the value 0. So we get only one point on our locus over the new origin, and it's a branch point because the new equation is the same as the old one.
So the locus near z tilde equals 0 looks like this. The branch point is the point 0, 0 in the new variables, which is infinity, infinity in the old variables. And of course, we've just got another disk. So we've got the locus for the whole of the compactified z-plane in two pieces, disks. To put them together, since these boundary circles are identified to give the z-sphere, we have to glue the two pieces along the upstairs boundaries. Therefore, we're gluing two disks along their boundaries, which gives another sphere. So the locus over the z-sphere is itself a sphere.
Let's now deform the locus sphere so that the points lie radially above the corresponding z points. This half has to cover the southern hemisphere, so we just curve it upwards. And here it is covering the z sphere, or at least half of it. To get the full compactified locus, we have to take this piece, turn it upside down, and deform it to cover the northern hemisphere. And here's the full compactified locus. It's in two pieces, which have to be identified along their common spiral edges. When we do this, we get a twofold covering of the z sphere, except for the branch points at the bottom and at the top, each of which, of course, just give us a single root. And when we stick the two halves together, here's what it looks like. We've cut a hole out so that you can see inside. Actually, I should say we've cut two holes out of it, because this disk is attached to the middle circle, and these two half disks are attached with this edge here, the farther edge along here, and the two half disks form a whole disk when their dotted edges are identified.
So we've seen that the compactified locus of the equation w squared equals z is a topological sphere. And actually it tells us quite a lot about the equation. First of all, we can see immediately that there are two square roots of z everywhere except z equals 0 and z equals infinity, where there's only one root in each case. And the fact that we have branch points at those points reflects a very important property of the equation, and it's this. If you go round any circle enclosing z equals infinity or z equals 0, the square roots get interchanged. Once round, and you change continuously from one square root to the other. Twice round, and you get back where you started. And that completes a single circle on the locus. And that's really why the locus here is a disk, because it's made up of all those circles. By the way, if your little circle doesn't surround z equals 0 or infinity, the roots don't swap. For example, let's take this point and this root. As we go round the circle, we come back to the same root.
For the rest of the program, we look at a different quadratic equation which gives a more complicated locus. In fact, the locus of this equation is as complicated as you can get for a complex conic. Let's first factorize the right-hand side, and we'll use this notation to denote either of the two square roots. But we know that one root is minus the other, so we can write w like this. So again, we have two values of w for each z, except for z equals 0 and 1, where we have only one root, w equals 0 in each case. In fact, we get a branch point in each case. Consider z equals 0 first. And remember what's required for a branch point over z equals 0. If z goes round a little circle, centre 0 downstairs, then upstairs, the roots get swapped. So I need to show that these roots get swapped when z goes round such a circle. I'll do that by looking at the two factors of w separately. And I'm going to show that this factor swaps to minus itself, whereas this one comes back to its original value. That will prove that the product of these, the value of w, swaps to the second root, minus itself. So taking the root z factor first, we know how this behaves from our old locus, because that dealt precisely with the square roots of z.
And we've seen that the roots of z do swap over when you go round a little circle surrounding 0. Now what about the other factor, root z minus 1? Well, we can use our old locus again. Take the centre of this little circle as z equals minus 1. Then as z goes round a little circle, centre 0, z minus 1 takes values on this circle. And we can see that whichever route you choose upstairs, you come back to the same root. The roots don't swap.
So the roots of z swap, but the roots of z minus 1 don't. So when these are multiplied, the result is that the roots of z minus 1 do swap, which shows that z equals 0 gives a branch point. And a similar argument shows that z equals 1 also gives a branch point. You can look at that for yourself later.
So here's what the locus looks like above small disks, centre 0 and 1. Branch points above 0 and 1. What about the values of z outside the two disks? Let's take a strip of values along the x-axis, for example, between the two disks. For each value between the two disks, there are two roots, and each root varies continuously as z varies. So we must have two continuous strips joining the two regions of our locus. And if we now broaden those strips, we get a surface like this. Of course, you still have to identify this edge with this one, and this edge here with this one. And of course, the whole surface extends outwards indefinitely. But what about the compactified version? What happens at infinity?
Well, if you applied the algebraic trick, putting 1 over z equal to z tilde, etc., you'd find that z equals infinity is again a point where there's only one root, w equals infinity. In other words, there's only one point on the locus corresponding to z equals infinity. So that's a third funny point on the locus, in addition to the two branch points above 0 and 1. But this third point is not, in fact, a branch point. To see that, look again at this region of the locus. The missing part, out here, covers a neighbourhood of infinity. We can see what it looks like if we first deform this into something you've seen before. Our old compactified locus, a sphere, remember, with two disks missing. You just have to bend this upwards and over. And here it is, covering our z-sphere. We've put infinity here because, as I said, the missing region covers a neighbourhood of infinity. And you have to imagine that the two branch points, this one and the one underneath, are over the points 0 and 1. Now, what does the missing bit look like? Well, we know it's a double cover everywhere except over infinity, where there's only one point. We can see that's not a branch point, because we know a branch point has a disk-like neighbourhood. And this missing neighbourhood can't be a disk because it has two boundary components. This circle is one boundary component, and these two half circles make a second one, because their ends have to be identified. In fact, this missing region is what we promised you earlier. Two disks meeting in a point. Why is that? Well, the missing region is swept out by its two boundary circles as they move towards infinity. So we get two disks swept out, except at infinity where the two disks meet. And we call that point a pinch point. If it wasn't for the pinch point, we'd have two separate disks to glue in here, which would give us exactly what we had for our first example, a sphere. And for that reason, we call the compactified locus of w squared equals z squared minus z a pinched sphere. So, to summarize, we've seen that the locus of one type of quadratic can be displayed as a sphere, which double covers the z-sphere and is branched over 2 points. On the other hand, the locus of our second example was a double cover except at 3 points. 2 were branch points, the third was a pinch point, and the locus was a pinched sphere. In the next program, you'll see an example of a cubic equation whose locus is actually a torus. But for a conic, you always get a sphere or a pinched sphere.